Hello again students and welcome to another GCSE Computer Science theory lesson. This video is going to be on Unit 3, binary units and number bases. And we're talking about number bases, not this type of base. Okay, so binary units. Okay, so you need to be aware that a bit is the smallest unit of information that you can have on a computer. So it's just a single binary digit. In fact, that's what bit means. It's a portmanteau, or however you pronounce that word. It's a combination of two words, binary digit, bit for short. So that can be a 1 or a 0. A byte is 8 bits. An example, 01110011. There you go, there's an example of a byte. You're probably thinking, but why is it 8? Why not just go for 10 or 12 or 11 if you're feeling really sadistic? The short answer, because some dude in the 50s said so. I suppose at the time it just seemed like a nice whole number to work with. Kilobytes, well that's just 1,000 bytes. A megabyte is just 1,000 kilobytes. A gigabyte is 1,000 megabytes. And a terabyte is 1,000 gigabytes. And some of you are probably having a bit of a nerd rage watching this, thinking, oh, Mr. Roberts, there's actually 1,024 megabytes in a kilobyte. Well, yeah, you're sort of right, but I don't know. The exam board says you can do it in 1,000. Just keep things simple. Nobody really cares about that little 24 there. Just keep things simple. Call it 1,000. That's still correct as far as the exam's concerned. Okay then, you ready for the answer? Here it is. So, the next number in the sequence here would be 256. There we go. Alrighty then, now we need to just figure out which numbers in this list do we need to add together to make 300. Now straight away, I think it's a safe bet to say we're probably going to need 256. And now we just need 44, the number 44 left counted for. So, well, this is much bigger than 44, so that's no good. That's bigger than 44, nope. This is smaller than 44, so we'll probably need that. So what's 44 minus 32? That is 12. Now we just need to make up the number 12. So we don't need that. Yeah, we need 8. That's 12 minus 8. That's 4. We've got 4 left. Brilliant. We've got a 4 here. Fantastic. There we go. And that's the number 300 in binary. And if you want, you can just give this a pause, add all these numbers together, just to double check I've not made a maths error. Okay, so next up we're going to talk about the base 10 number system, also known as decimal, and some strange people like to call it Deanery. Alright then, so to understand this fully, we need to take a trip down memory lane and return to primary school for a brief moment. Good old primary school. It seemed like an endless stream of paper towels, spelling simple words, and once in a blue moon bringing out that weird smelly parachute. And I don't know why we ever brought out a parachute in primary school. If anybody knows, do let me know the answer to that. Alright, just one of life's mysteries we'll chalk that up to. Anyway, back on track. The base 10 number system. I'm going to switch to Paint so I can do some nice drawings for you. Okay, the base 10 number system. Okay, let's say we were going to write out the number 205 in base 10. Well, you just write out 205. There you go. Base 10, you've been using it since you were in primary school. You've probably been using it before that. Base 10 is the system that people use all of the time. Why is it called base 10? Because these columns we multiply by 10 every time we go across. Look at that, times by 10. Base 10 times by 10. That is why. I want you to have a think about, why is it that humans use base 10? Is it a coincidence that we happen to use a number system that is based around the unit 10? Or is there a reason why? I mean, 2,000 years ago, or 4,000 years ago, whenever it was, when humans started using numbers 0 through to 9, what was the rationale for that? Why do we find the number 10 so easy to work with? Okay, the reason for that is because we have 10 digits on our hands. Well, at least most of us do. I'm sure there's some people in Wales with 12 fingers on account of all the inbreeding and all that stuff. Anyway, moving on. Base 2, aka binary. Binary is used by computers. The reason why computers use binary is because they don't have hands. Yep, I'm being serious. Did you know your computer does not have hands? Yeah, okay, I'll just give you a second to comprehend that. Instead, a computer only understands two numbers, 0 and 1. On or off, high voltage or low voltage. I'm going to show you something that's going to blow your mind. Give me a second. Look at that. There's a power switch. Can you see that the 0 means off and the 1 means on? You'll never look at a power switch the same way again. Okay, so how do we convert decimal numbers into binary? Well, let me start off by putting this into Microsoft Paint. Okay, let's say we wanted to represent the number, I don't know, 5. The number 5 in binary. Well, we just find out which numbers in this list do we need to make the number 5. And you might have correctly spotted that we need the number 4 and the number 1. So add those together, we get the number 5. Make the rest of them zeros. And there you have it. There is the number 5 in binary. Easy peasy. Let's try a slightly more complex example. I want you to tell me what number this is when I've finished writing it in. What number is this? Pause the video if you need a few more minutes to figure it out. Okay, so to get this number, we just add 64 to 16, which is 80. So there you go, your answer there is 80. I'll just do one more example, just to be on the safe side here. I want you to represent the number 300. Ooh. That's going to be a really tricky number to represent, so you're definitely going to have to pause this video. But before you pause it, let me just give you a clue. Okay, pause this video and give this a try. Okay, so next up we're going to talk about base 16, also known as hexadecimal, or hex for short. And before continuing on with this topic, I recommend taking a small break and getting yourself a cup of coffee, because this is going to be a lot of content for this topic. Unless, of course, you're in the classroom, then you're probably not allowed to have a cup of coffee. But then again, why are you watching this in the classroom? Why isn't your teacher teaching you this topic? It's something to challenge them on. Unless, of course, I'm your teacher, then in that case, don't challenge me, shut up and do the work. Okay, let's get started. Base 16. There are, well, the reason why it's called base 16 is because these things, they go up in units of 16. So we times by 16 each time. And if you don't believe me, you can double check that 16 times 16 is 256. The other reason why this is called base 16 is because we can have 16 different digits inside each column. And I'll just clarify that by bringing in the other number bases. So with base 10, you can have 10 different digits inside each column. So you can have 0 through to 9 here, that's 10 digits. And with base 2, you can have 2 different digits, that's 0 through to 1. And likewise with base 16, you can have 16 different digits, that's 0 through to 15. Or rather, 15 through to F. Confusing? Don't worry, I'll go through it. So we'll start off by counting to the number 15 in hexadecimal, or more accurately, counting to the number F in hexadecimal. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15. And we're stopping at 15. You probably think, oh, base 16, shouldn't we stop at 16? Well, it's base 16 because there are 16 digits including 0. So we start at 0, including 0, there are 16. So f is equal to 15. Okay, now I'm just going to throw you straight in to an example question. I want you to figure out what this number is. So we've got b in this column and 2 in this column. We're going to convert this into decimal. Now, if you're feeling brave enough to try this yourself, pause this video and give it a go, but otherwise carry on watching and I'm going to talk you through the process. Okay, so first of all, we know that there are 2 lots of 16 and b lots of 1. So let's do 2 times by 16 plus b times by 1. Now we need to figure out what b is. Well, b means 11. So b means 11. So we're going to do 11 times 1. Well, if you times something by 1, it's just itself. So there's our answer. It's 2 times 16 plus 11. Well, 2 times 16 is 32. 32 plus 11 is 43. So there you have it. Okay, confused? Let's try another one. And I'm just going to go ahead and delete this really big number because you're not going to be asked to do anything that big in the exam. So I'm just going to delete all of that. Okay, let's try a different number, a more complicated one. So let's try DF. So the number DF in hexadecimal, we're going to convert that into base 10. So to start off with, there are D lots of 16. So D times 16, and we're going to add F times 1. So there are F lots of 1. Okay, so there's our answer. Well, part of our answer. Well, let's first of all figure out what D is. Well, D is, well, if you forget what it is, you can just count 9, 10, 11, 12, 13. So D is 13, so that's going to be 13 times by 16 plus F. F is 15. So 15 times by 1. And then we just do the maths on that, and we can have our answer. Now, you're not allowed a calculator in the exam, but just for the purposes of this lesson, you are welcome to use a calculator because I'm more concerned with you learning something as opposed to being able to do mental arithmetic. Let's do 13 times by 16, which is equal to 208. And 15 times by 1, 15. Oh, well, I must be tired if I'm having to type 15 times 1 into a calculator. And let's add those two together, which is 223. And I'm just going to double check that this is correct by looking it up on the internet. So what was our question? It was DF. So the answer was 223. Is that what we put? Yeah, brilliant. There we go. Now it gets a little bit more tricky if we try and do this in reverse. So if I gave you a number and asked you to convert it into hex, this is where it gets tricky. So if I said, I have a number, it is 20. What is 20 in hexadecimal? Just pause this video and see if you can figure it out. Okay, now some of you might be able to look at this and just instantly go, okay, I know what that is, easy peasy. For others, it might not be so obvious. So I'm going to have a step-by-step approach to help you out. So we're going to start off with the left here, 16s, and then we're going to move on to the ones. Well, first of all, how many 16s can we fit into 20? Well, we can fit 1 in there with 4 left over. So that's just going to be 1 and 4. So there you go. So we can fit 1 16 in there with 4 ones left over. Easy peasy. let's try a more complex example. I'm just going to give you a really big random number here, and it's going to be painful. 201. There you go. Pause this video and give it a try, please. Okay, are you ready? Let's go through it. So, how many 16s can we fit into 201? I'm just going to guess some random numbers here. Okay, so I'm just going to do 12 times 16. That was pretty close. Okay, so we can fit 12 16s in there. So we can fit 12 16s. And that gives us a total of 192. And what's 101 minus 192? So there you go, there's 9 left over. So that's 12 with 9 left over. So there we have it. That's going to be 12 with 9 left over. Ooh, hang on, we've done something wrong. It's not 12, is it? So A is 10, B is 11, C is 12, so this is actually going to be C9. So there you have it, C9. And let me just double check that this is correct. Okay, 201. There you go. That is reassuring that I know what I'm doing. Right, so you're probably thinking, what is the point in hexadecimal? You probably think, I can kind of see the point in binary because computers only understand ons and offs. Or I understand the point in base 10 because we got 10 digits. So why are we using something called base 16? Why does it exist? What is the significance of that in computer science? Well, allow me to show you by converting a hexadecimal number into binary. So I'm going to take a different number. I'm just going to make one up here. Let's take 4 and 8 by here. So let's convert this number into binary, and it is very, very, very easy to do. So to start off with, we're just going to write out the number system for a 4-bit binary number. So 1, 2, 4, and 8. And 1, 2, 4, and 8 by here. And we're just going to represent each of these numbers as binary. So what is 8 in binary? It's going to be 1, 0, 0. And what is 4 in binary? It is just 0, 1, 0, 0. And there you have it. That's how you convert hexadecimal into binary. We just mush these things together. And there you have it. There is your hexadecimal number written in binary really easily. So this is why we use hexadecimal in computer science. It is a very easy way for humans to write down binary as a shortened version. At this stage in your programming career, GCSE level, you're probably thinking that is not easier to represent binary. Oh, but it is. Just trust me on that. It is definitely a much easier shorthand way of writing down binary numbers. If you really don't believe me, let's look at some color codes in HTML. Okay, so if we look at that, there is hexadecimal there. That is the same thing as writing out 8 ones for this section, followed by another 8, followed by another 8. So that's the same as writing down 24 binary digits. And you have to admit, writing down just 6 characters is a much simpler shorthand version of that. And by the way, that FF stands for 255. So one last thing that you should be aware of before we go, and I was waiting until the end of this video before telling you about this. Going back up to binary units, there is one more unit that I didn't mention, and it is called a nibble, which is only 4 bits. And there must have been some kind of programming joke going on when they called it a nibble, because a nibble is just half of a byte. So that's just 4 bits, aka a single hex digit. Hexadecimal, the reason why we use it, it's a shortened version, it's a shorthand way of writing binary, it's easier for humans to read, but also each hex digit represents a nibble or 4 bits.